Good morning, good afternoon, good evening, everyone. This is Diane Fodell. Thank you for the Cognitive Systems Institute Speaker Series. Today, I am pleased to welcome back Richard Waldinger, a researcher in SRI's International Artificial Intelligence Center. This is Richard's second appearance on our program. He is gracious enough to come back to present to us. I'm afraid we had some technical difficulties during his first presentation, which cut his time in half for interaction from the audience. Richard's work is renowned in the area of artificial intelligence and in reasoning, which is so difficult and so important. Richard's interests focus on the application of automated deduction to problems in software engineering and artificial intelligence. He's worked in program verification and synthesis, automatic planning, and question answering. He's a co-author of a series of textbooks on deductive aspects of computer programming, and his PhD thesis was one of the first on program synthesis. Richard, thank you very much for being here, and I will turn the call over to you.
Okay, thank you, Diane. Thank you for that nice introduction. And this will be a talk similar to what I did a few weeks ago, but I should be able to talk slower since I have twice as much time. And let me get this full screened. Here's that button. Anyway, I don't see the full screen button now, so I'll let it go this way. This is reporting on. No, that's not it. I better. Okay, this is joint work with, it's a team project with Cleo Kondrabi, a linguist at Stanford, Kyle Richardson, a PhD candidate in computational linguistics at Stuttgart, Osman Sunbul, who is a researcher at SAP, and Vishal Sikka, who was at SAP and is now the CEO of Infosys. And it's the work is about question answering. Our interest is in accessing knowledge from structured data sources using natural language as our interface. So we're formulating questions in natural language, such as English, and expect to be able to get the answers by accessing structured data sources. Now, this is a hard problem. For one thing, we're talking about an uncontrolled natural language. So we're not talking about restricted English. We're talking about ordinary, common English that everyone knows. And we are not looking up websites the way Google is. We want to get actual answers to the questions, specific answers. And we are getting answers which may not be explicitly in a database, but might need to be deduced or computed from information in the database. And we're not limiting ourselves to a single database. We want to access multiple databases which may not be meant to be used together. And we're accepting questions which are not just a single question, but a sequence of questions, each one referring back to previous questions in the sequence. So you ask one question, you get some answers, you want to restrict the question, you want to extend the question, so you ask an add-on question, and you want to be able to refer back to things that you mentioned in the previous question. So at this point, let me go ahead and show a video that Kyle Richardson did of the use of our system. I won't show the whole video, I'll just show the beginning so you can get to see samples. It's a little bit small, but I'll say, "Hi Quest, can you give me a list of SAP clients from our database?" And it gives us a list of questions, and it gives some other information that I'll explain, but we get a list of companies from the database. And then you want to ask a question about one particular company. So in particular, I'm interested in the Beck Sports Company. Can you pull up a profile of Beck Sports that includes debt information and country of origin? So you want more information about a particular company, Beck Sports. So it tells you that Beck Sports is Irish, and that it gives you its debt information.
Excuse me, Richard.
So,
Background noise. Is that where you are?
No, I hear the noise over the line, but it's not here.
Okay, audience, please mute.
Okay, now it's quiet.
Okay, it says they're unmuted now, but I just asked everybody to go on mute. I'm sorry for the interruption.
Okay.
Go ahead, Richard.
As I was saying, this is a difficult question because of the unrestricted English, the continued questions, but we are making the problem more tractable by restricting ourselves to a particular subject domain that we understand well. So we are, in this case, we're restricting ourselves to a business enterprise domain, and the information that we're accessing comes from SAP's HANA database and a number of other sources of structured information, such as currency exchange information, like how many euros in a dollar and stuff like that. And the system that we developed to illustrate this is called Quest, and it's work in progress, but Kyle is showing you access to Quest in this in his video, and I'll show more of the Quest demo at the end. So here's a sample query sequence. Show a company with a long-term debt within the last 2 years. And you may see some companies that satisfy that. They have a long-term debt more than a certain length of time, but it's all within the last 2 years. And then we say we are only interested in companies with a really big debt of more than 5 million euros. So that's additional information. We may see fewer companies in our list because we only want big debtors. And then we decide we're only interested in Swiss companies, so we say, the company must be Swiss, or it must be Swiss. And that will give us a smaller list of companies, only the Swiss ones. So we have a sort of a dialogue with the system where we add more and more constraints and ask for additional information. Now, this kind of problem cannot simply be done by table lookup, like translating from the query directly into a database access. We have to do some reasoning to figure out what information is being required. The query itself might be logically complex. It might contain logical operators like and, or quantifiers like for all and exists. The query might be ambiguous, and we might need to use reasoning about domain knowledge to decide which of the possible meanings is intended by the user. There might be a discrepancy in the vocabulary between the terminology that the user chooses and the terminology that's used in the database. There might need to be some reasoning to bridge the gap between the query and the information that's stored in the database. And we might need some reasoning also to put pieces, each database supplies little pieces of the answer. We might need reasoning to compose those into the big answer that the person really is requiring. So the approach that we're using combines parsing, natural language technology, and automated deduction. So we take the query and submit it to a semantic parser, which produces a semantic representation, which is a structure that captures the meaning of the query. This semantic representation is then transformed into a logical form. This is like a sentence in symbolic logic, which also captures the meaning of the query. And that question can be submitted to a theorem prover as a theorem to be proved. And we conduct the proof, and the theorem prover not only determines the truth of the theorem, but finds answers to the query, which are then extracted from the proof and presented to the user. So the proof is conducted over an axiomatic theory, which contains the information, our information about the subject. We don't talk about any old subject domain. We talk about a domain that we understand, which is in our axiomatic theory. And the theory has some information in it itself, but also it contains links to the relevant databases. So as we're conducting the proof, we can look things up in the database and get the answer and continue the proof, inserting the answer into our proof in progress. So in Quest, we use a parser that was written by Kyle Richardson, which is called the SAPL. It's a cascade parser, which translates the query into a semantic representation, which we then translate into a logical form. The logical form then goes to a theorem prover, in this case SRI's SNARK, which was implemented by the late Mark Stickle. The SNARK is hooked up via a mechanism called procedural attachment to data from from SAP's HANA database, and also from a variety of web sources such as the currency conversion information, knowledge about various countries and geographic information, and so on. SNARK, the theorem prover that we're using, is a general purpose theorem prover. It can reason about anything given the appropriate axiomatic theory. It's a resolution theorem prover. It does its general reasoning using a rule called the resolution principle. It has special rules for dealing with equality, paramodulation, and rewriting rules for equality. It's based on a unification that is sorted, so it knows about the sorts of the object it's talking about. It knows which symbols represent debts, which symbols represent companies, which symbols represent nationalities, and so forth. It has the capability for extracting answers from the proof, and it has the procedural attachment mechanism for linking symbols in the theory with tables in a database, and has special capabilities for spatial and temporal reasoning, which is appropriate for this particular subject domain. Now, it's crucial that we have a good axiomatic theory. Let me see if I can get to full. This might be a bit better. It's appropriate. We need to have an axiomatic subject domain theory, and what this theory does is it gives us definitions of the concepts in the query. It has axioms that express the capabilities of various databases. It has the background knowledge necessary to relate the query information, database information, and it's divided into two parts. One part gives the sorts, it's like the ontology. It gives the sorts and types of all the symbols and in the theory, and what the types of various relations and function symbols in the theory. And it has axioms, which are declarative sentences in logic, which provides subject domain knowledge. The sort structure, which is used both for reasoning and for parsing, in this case is divided into we have a very general category called entities. Almost everything is an entity, which includes subtypes like agents and time intervals and numbers. Agents include companies and could also include individuals. Debt is regarded as a time interval, so this is debt is of sort of time. And then there are numbers like the amount of a debt is an amount of money, which is a number. The size of a company is like the number of employees, which is also a number. Now, for the relations that we use for describing the subject knowledge, we know about the sort information associated with each relation. So the company has debt relation is a relation between a company and its debt. The company has size is a relation between the company and its size, which is a number. The within relation is a relation between two time intervals, and information like nationality is a property of agents. So people and companies can have nationalities. The parsing, originally we worked with PARC, and we used the PARC's natural language technology, including XLE and Bridge. And those were natural language components that we used. But then Kyle developed a new parser which was particularly appropriate for our domain, which is called SAPL. And the parser is informed by the sort structure of the subject domain, and that's useful for parsing and for disambiguation. So, like, here's an example. We have a query such as show a company with a high debt within the last 2 years, and this becomes the semantic representation, which tells us what the variables are, the company and the debt, and it gives us scoping information about the quantifiers. The company has a higher scope than the debt, and this isn't a complete semantic representation, it's just a part. But from this semantic representation, we can mechanically construct a logical form. Now, this is a sentence in logic which reflects the meaning of our query. So we want to find company, debt, and time intervals where the company has the debt. The debt is within the time interval. The time interval is of length 2 years and extends from the beginning of the debt until now. Now is a fictitious time that we're using to ask our question. Now, here's an axiom that gives us information about what it means to have a high debt. High debt is there's no general concept of a high number, but a high debt we arbitrarily define as being more than $1 million US. Now, if we want to change the meaning of high, we can just replace the axiom with another axiom. Now, here is an axiom which defines what it means for a company to have a debt, what it means for a company to owe money to SAP. This is a client of SAP that owes SAP money. And it says to determine what, whether the company has a debt, we look up its balance in the database, the HANA database, and we look up the balance of this company in the database, and we determine that this balance is positive, because a debt will be regarded as a positive number. That's the second argument of the company record. If it has zero balance, then it does not have a debt. If it has negative balance, then SAP actually owes the company money, so it has no debt at all. And this linkage, the company record, is linked to the actual database by the procedural attachment mechanism. And here is a depiction of the row in the database that, well, it's just part of it. There are actually something like 800 entries in the database for each company. it has the balance, the amount of money in its balance. Its location, CH, is a code for Switzerland, and the date is the date the debt was incurred is September 1st, 2007. So when the proof is conducted using this and other axioms, and when we get finish the proof, we have actually found in the database the information that we want. And we also can construct from the proof an explanation of why this answer is a good answer. So we have SL Food has a debt which is high. It's within the appropriate time interval between the incursion of the debt, the 2 years from now. Now is September 1st, 2008 in our fictitious time. The duration of this interval is 2 years, so the debt is within this 2-year period, and the interval extends from 2 years ago till now. Now we use reasoning to. How am I doing for time, Dan? Is it? I don't see.
You're good. It's 10:52 Eastern Time, 7:52 your time. So if you finish in the next couple minutes, we can have 5 minutes for questions and answers.
Okay. We use reasoning for, among other things, resolving ambiguity. So if I say, show me a client with a high debt, and then we go on and say, it was within the last 2 years, the it must refer to the debt, because debts are temporal objects. Debts are of sort time, so to be within the last 2 years, it has to be within sort time. Whereas if we say, oh, it should be Swiss, so we want to find something that's Swiss, then it must refer to the client, because the client has client has nationality, but debts do not have nationality in our ontology. So this is one way in which reasoning becomes crucial, and just sort reasoning becomes crucial in figuring out what the sentence means. A sentence might have many meanings. The parser might give it many meanings, but the sort will restrict us to a meaning which makes sense in our subject domain. Our current work involves translating. The system currently translates queries into logical form. We can use the same technology to translate declarative English sentences into logical form, and that gives us a way to allow a domain expert who doesn't know anything about logic or databases or programming to extend the theory by providing it with new information. So I think at this point I will stop and see if there are any questions that I can handle at this time.
Thank you, Richard. Thanks for putting your picture back up, too. So, audience, I have muted and unmuted everybody a couple times, so you may have to toggle *1 if you are on the phone. If you're using your computer for audio, there's a little microphone button that's muted, and you can press that and unmute it to ask some questions of Richard.
Hi, Richard. Hi, Richard. This is Jim Spoor. I think I'm unmuted now. Can you hear me?
Yes,
right. Let me. I have a. Yeah, I can hear you.
Okay, great. Thanks.
Hi, Jim.
I had to hit *1. Hi. Thanks again. Great talk. Just really thought-provoking. I'm wondering, and I think I may have asked this the last time, but I'm going to ask it again. Have you coupled any learning components to this? So have you tried to interface any machine learning, create data sets, and have machine learning as part of it?
Kyle, he's the PhD candidate at Stuttgart, is interested in using learning from corpuses of data to infer the information necessary to parse sentences in a new domain. So we would be able to take a new domain and instantiate the parser so that it will not need to be tailored specifically to that new domain, but will be able to get looking at huge samples of questions and answers. And he's been doing this in the Unix domain, which is a somewhat different domain than the business domain that his thesis is involved in. I don't know whether Kyle is here, but he knows more about this. Now, for learning axioms, this so far what we're doing is not learning axioms from samples of text, but from taking text which is specially intended to teach the system. So it's a teachable system rather than a system that goes out on the web and learns information.
Okay, great. Thank you very much, Richard. Others, comments or questions?
Yeah, hi, this is Sue Feldman. Can you hear me?
Hi, yes, I hear you.
Yeah, hi. Just a great presentation, exactly what we're interested in. Could you talk a little bit about the process of mapping among those multiple sources with differing terminology, as well as, of course, I'd be more interested in learning more about the process of teaching the system, because it seems highly manual at this point. I'm wondering how you're working on automating that.
Yes. So your first part of your question is the process of how we use the subject domain knowledge to disambiguate the query. Well,
correct.
The parser will get many.
I'm sorry, it's more than that. It's the fact that, you've got client in one database and customer in another, and ID number in the third. And one assumes you could use a certain amount of inferencing so that you don't have to create a reference ontology or something very painful like that, but I'm not sure.
Yeah, we do have axioms which will tell us that client is the same thing as customer. So that is just a piece of subject domain knowledge that we have to tell the system. And the relationship between ID numbers and names of clients is also something that's axiomatized. So that presently that has to be done by hand. It's a time-consuming and laborious process, and also something that requires a certain amount of knowledge of logic in the system to be able to do it correctly. Now, what we intend to do, which we haven't done yet, is allow this to be done in English, which isn't the same as not having to do it at all, but it allows someone to describe the knowledge without having to write it in logic or in the programming language. Mm-hmm. And then we take that English and we translate it into logic using the same technology we use to translate queries. Mm-hmm. And this is not done yet. This is our part of our continued work. It's not currently the system doesn't currently let you extend the theory by saying things in English, but that's something that we intend to do.
Yeah, that would be really useful, across cognitive computing.
Oh, sure, because it's very, otherwise it's not realistic to expect huge bodies of knowledge to be translated into axiomatic theories. It's something, but it's an active area of natural language research to be able to take declarative text and construct logical forms for it.
Yeah, thank you.
Thanks for your question.
Thank you. We're just about out of time. If anybody has a real quick question, we'll go one more minute. Otherwise, we'll carry on with the questions and answers on our LinkedIn discussion group.
Richard, this is Scott McLeod. Thank you for a great talk. I'm curious if you've begun to develop in your interactions with other databases with the Wikidata database written for Wikipedia's 300 languages interlingually. It's also developing with AI and would be a remarkable resource for possible, I think, for your work. Have you engaged Wikidata at all?
No, we haven't, and as you're saying, that would be a really valuable source of information. Something that we would like to do. There's other things. There's the Sumo ontology, which is a huge repository of information containing 80,000 axioms, all already in logical form, which would be extremely valuable. But so far we haven't integrated that. There, this is just what we're reporting is just less than a year of work. So there's a lot more we could do with if we continue in this direction.
Thank you.
Thank you for your questions, audience, and thank you, Richard, for a great presentation and for coming back and taking us through in more detail the work that you've been doing. Great work.
Okay, thank you.
Thank you all for attending, and we will see you next week. Thank you, Richard.
Okay, thanks. Bye-bye.